All right, guys, today we are going to go ahead and continue working in section 7.1. Today we get to do like some real life stuff. We will need Desmos.com. So if you want to have another source of technology with you, I just grabbed my phone so I could walk you through the steps. But what we're going to do is model growth and decay various situations. And here is our formula, okay? So A of t, this is the final amount after a given time. So whether we're looking at weeks, years, months, hours, minutes, this would be our final amount. Now, A is the initial amount. So we are going to look at scenarios like you are investing money in a bank. So A would be, well, how much did you invest? Or maybe we'll look at how much money a house is worth. So A would be at the time that we are looking, so at the beginning, what was the value of the house, okay? Then in parentheses, it's always 1. 1 represents 100% of the initial value. Now, if you're looking at something that's exponential growth, you will be adding R. Now, R is a percentage. It is your rate of increase. And remember, whenever you are dealing with percents in math, you always want to make sure that you turn it into a decimal first. Okay, then you have your exponent, which is T. T is representing the number of time periods. So again, how many years, weeks, days, depending on the scenario. Now, not everything grows in value. Sometimes we have a decay or a decrease. So maybe you bought a four-wheeler, right? So A is, well, how much did you spend on the four-wheeler? 1 is 100% of what it was worth. The value of a four-wheeler, you guys, it's a bummer deal, but it goes down. So you would be minusing whatever the percent of value that you lose per year, and your exponent would be that T. Okay, so just kind of showing you that it is both growth and decay. If you end up adding, that would be called the growth factor because it's exponential growth. Because if I have 1 plus a value, your base, because that's where your exponent is, your base would be greater than 1, so it's exponential growth. In a similar fashion, if you have 1 minus R, that would be exponential decay, so this value is called your decay factor. As we go to Desmos, one thing you want to remember, even though in the formula our variable is a t because it's representing time, you have to use x on Desmos, okay? So let's go ahead and do a few of these. So here, our first situation, we have Clara. And Clara invests $5,000 in an account, and that account pays her 6.25% interest every year. After how many years will her investment be worth $10,000? So we are writing a function to model the growth. Okay, so the original amount. Clara invests $5,000. So that's that A value. Then it's always the number 1. It says that she is gaining interest, okay? So we know she's gaining, so it's plus your percentage, 6.25% is 0.0625. That goes to the power of t, but I know I'm going to Desmos.com, so I'm just going to go ahead and put an x right now. We want to know when will it equal $10,000. So our initial value, 1, it's growing, so plus. Your interest rate is a decimal. This goes in parentheses to the power of x or t. We want to know when it equals 10,000. Okay, so as we go to Desmos.com, the main thing here is that you have to realize that you're going to have to set the window. Okay, so remember, you go to that little tool in the corner. Your x-axis, your x value is the number of years. Okay, so you can't have a negative amount of years. 0 is the day that Clara brings that $5,000 into the bank. I'm thinking, and again, this is a guessing game. If we don't find our solution, I'm going to go ahead and say within 20 years, I think it would be up to 10,000. I might be way off. I'm a math teacher, not a banker. Okay, so I'm going to guess 20. Now, your y-axis is money. Obviously, the lowest that she's going to have is 5,000 because that's how much money she is putting in the bank. We want to know when it gets to 10,000. So guys, I'm going to have this go up to 11,000 because I want to make sure that I can see it. If I go to 10,000, that's going to be at the very, very top. So step 1, you want to go ahead and set your window. So we did that. Now, you have to graph these two portions. Oh, sorry, now I'm going to zoom out. These two portions separately. This will be an exponential curve, and I'll show you what I mean. So if I have 5,000, that's what Clara put in the bank. It's always a parenthesis, 1 plus 0.0625, close it to the power of, and again, you have to do x. So there's the curve. We want to find an intersection. We want to know when this equals 10,000. So check this out. I can go y equals 10,000, and it's going to give me a line right there. One really, really weird thing with Desmos, you guys, when you're doing 10,000, if you happen to go 10,000, it doesn't work. I don't understand why, but just type the 10,000 without the comma. Now, if you'll notice, I do have the point right here. That is your solution. Your y value represents the amount of money. The x value is your time in years. So Clara, in 11.433 years, her $5,000 investment is now $10,000. So that would be our solution. It says use the graph to predict when the value of the investment will reach $10,000. It'll be approximately 11.4 years, and that's it. So being able to take a real-life scenario, write it as an exponential equation, then you graph each side into Desmos separately. This has to have a y equals with it, and again, don't put in the commas. You look for their intersection point. The x value is going to answer the question. So let's do some more, okay, just because this is fun. Here's our next scenario. In the year 1981, that was the year I learned how to walk, just in case you were curious. Okay, in the year 1981, the Australian humpback whale population was 350, and it increased at a rate of 14% every year since then, okay? So we can already write the left side of our function. How many whale do we have at the beginning? Well, Australian humpback whale population was 350. So at the beginning, that's what we had. Then it's 1. It is increasing, so it's plus. 14% is 0.14. To the power of t, because it's per year, I'm going to put in an x, so I'm ready to go for Desmos, okay? We want to know, it says use a graph, so we're going to Desmos, to predict when the population, oh my goodness, will reach 20,000. That's crazy. So right now, there's 350 of these Australian humpback whales. If it's growing 14% per year, we want to know how many years until there's 20,000. So again, go back to Desmos. Yeah. Hit that little tool. We got to figure out, okay, what makes sense here? Obviously, 0. You can't have a negative amount of time. I could be totally wrong again. Hey, last time it worked, but I'm going to say it's going to take at least 25 years. I'm going more than that. I'm thinking 30, okay? We're starting with 350. We want to know when is it going to hit 20,000. And again, let's say that we set our window like this and by chance we don't see where the intersection is. You can always just hit that tool and go back and reset your window. So that's kind of the fun part. It's a little bit of a guessing game. We're doing like science. You're doing a hypothesis and then we're going to test it. 350 starting amount of whale plus 1 plus 0.14, close it to the power of, make sure you use an x. Hey, look at that curve. Oh boy, we're not going to see this. Okay, and it's y equals, we want to know when there's 20,000. Don't put a comma. Okay, so at this point, see, I told you that. I didn't know. But the cool thing is with Desmos, I can just go ahead and slide. So my window was not technically where it needed to be, but I slid that over. Here's my intersection point. You go ahead, tap on that point, and there's your solution. The population of the humpback whale is at 20,000, 30.875 years after 1981 is when they started watching that population. So how long is it going to take? It's going to take approximately 30.875, so I'm going to say 30.9 years. You could even say approximately 31 years is how long it would take. That's kind of crazy, though, when you think about it. Only 31 years to go from 350 to 20,000. Super cool. Hope you guys are enjoying this. To me, I love this real-life stuff. Okay, couple more. You can also use this type of math to try to make estimations for city populations. So that's where we're going to go right now. A city population, which initially the population was 15,500. It's been dropping, okay? So we have some exponential decay here. The value is going down. It is dropping 3% a year. Write an exponential function and graph the function. Use the graph to predict when the population will drop below 8,000. Okay, so you're starting with 15,500. It's always the number 1. Our value is dropping, so it's minus 0.03 because it's 3%. Close the parentheses. There is my exponent. That's my variable. We want to know when it's going to drop below 8,000. So I'm going to set it equal to 8,000, and that way I'll know when it hits that value. It's going to go below it anytime after because this shows us it is continuously dropping. So again, time to go to Desmos. I'm going to get rid of my last graph. Okay, I'll hit the little wrench. We got to set our windows. Okay, so X value, again, we're looking at time 0 because we can't have a negative amount of time. Right now we have 15,000 plus people. We want to know when it's down to 8,000, but it's not dropping that fast. It's only dropping like 3%. So I'm going to say let's try 20 just to see what happens. Okay, the lowest value that we're looking for is 8,000. So again, I'm going to go a little bit lower than that because I want to make sure that I can see the intersection. I don't want it to be like on an edge. So 7,000, the highest that I know it's going to go. There we go, buddy. The highest that it's going to go is 15,500. So if I set the window ready to go, now I'm going to enter in my exponential function. So 15,500, open a parenthesis, 1 minus 0.03 to the power of x. Whoa, okay, sweet. Now I'm going to go ahead and y equals 8,000. Oh, there we go. Okay, so there's the line. Hey, so right away it didn't look very promising. Like if you saw my curve, obviously it's going to grow faster than I think. But the cool thing is you can slide this around, and as soon as you find that intersection, something went wrong. 15,500 minus, oh, here we go, guys. That's what I did. My bad. If you saw this and you were yelling at your video, I am sorry. It's to the exponent. I just had it so it was multiplied by x. Terrible, terrible, terrible. Okay. There we go. Let's go back and do this. So my years, I said 0 to 20. And we are going to look 7,000 to, sorry, I hope I'm not holding too many of you guys up. 7,000 to 15,500. Now that looks way better. I was like, what is going on? Got to be careful how you put stuff in Desmos. Even after years of doing this, guys, I still make silly little mistakes too. All right, so here is our curve. And again, you can see that it's going downwards because the population of that city is going down. Here is my vertical line, or sorry, my horizontal line to show you where the intersection is. The population will reach 8,000 in 21.714 years. So it says, when will it be below 8,000? So we would say after approximately 21.7 years, because at 21.7 years, that's when it hits 8,000. It's going to continue to drop because it's exponential decay. So it's after this amount that we will get below 8,000. Just to make sure we've got it, we got to do, oh no, I got 2 more. Yes. Okay. I promise I'll be careful when I enter stuff in Desmos. Okay. A motor scooter purchased for $1,000, it depreciates. What depreciates means is that it loses its value. So we're looking at exponential decay. It depreciates at a pretty high percentage, 15%. Write an exponential function and graph the function. Use the graph to predict when it's going to fall below $100. So how sad. Let's say you buy a motor scooter and you're like, yeah, you drive it, you pay $1,000, you drive it for a while and like you're going to go sell it. There are times where you might not realize it, but the value has even dropped so low that it's like below $100. So we're going to see how long would that be. At the beginning, your motor scooter is worth $1,000. It's 1. It depreciates, so it's minus 0.15 to the power of x. When is it going to equal 100? So let's go ahead, go to Desmos, set our window. X is years. So 0 to... let's say 15. I mean, the value's dropping pretty quickly. So I'm going to say, you probably keep it for 15 years. The value at the beginning is 1,000, so that's the highest it's going to go. We want to know when it hits 100. So you guys, I'm just going to say 0 to 1,000 because again, I want to make sure I can see that intersection. So it's 1,000, that's the initial value, 1 minus 0.15, close it, to the power of x. Gotcha. Now I want to know when is the y value, the value equal to 100. So I went ahead, graphed it. There is my intersection point. I can go ahead, tap on that point, the 100, that's the value of your motor scooter. That's the time. So in 14.168 years, that's how many years it takes for the value to go from 1,000 all the way down to 100. They want to know when it's going to fall below that. So that means we are looking after approximately 14.168, so after approximately 14.2 years. So this is about when it will get to 100, so after that it will drop below. One more, just because I'm having a great time, you guys. I'm teaching from my classroom. I had to come in and, oh my gosh, it just made me so much happier. The only thing that would be better is if all of these seats were full and you were sitting here. So I'm just having to pretend, but it really is uplifting to be in the classroom. So let's do one more just for good measure. The value of a $3,000 computer decreases. So that's a true scenario. As you guys go off to college, you'll probably be buying a computer. You keep it for a couple years. If you go to sell it or trade it in, the value will go down from what you originally paid for the computer. Okay, so just like a real life scenario of when you do this. It decreases, this is a lot, 30% each year. So write a function for the computer's value. So it's starting at 3,000. That's its initial value. It's 1 minus, because it's decreasing. Your percentage is 30, so it's 0.30 to the power of x. So this is an exponential function where x is representing years, and it's going to give you the value that you still have on your computer. It says, does this function represent growth or decay? Well, this is decay, because if I look, the base, what goes with the exponent, is 1 minus 0.30. 1 minus 0.3 is 0.7. 0.7 is between 0 and 1. If you have exponential decay, that's what your base values. They're in between 0 and 1. Okay, so this is decay. It says use a graph to predict the value in 4 years. So here's one where you could just go ahead and go to Desmos, graph this in, and then you could go ahead and trace, and you want to get to 4 years. So I'll show you what that is. Otherwise, if they did not ask you to do a graph, you could just plug a 4 in and find the exact value. But the whole idea of the second part of 7.1 is being able to incorporate that graphing technology. So we will go ahead and graph this. So we have to set our window. This is time, so 0, and we are looking at 4 years, so I'm going to go ahead and just do 6. So 0 to 6, so I can make sure that I can see where that 4 is. The value of the computer, I'm going to say 0, because it won't be negative. And the highest it's going to be is 3,000. So again, just kind of make a window that you feel fits. If it doesn't work, you'll be able to change it or slide around on Desmos and see where those points are. I have 3,000, open a parenthesis, 1 minus 0.30, close it, to the power of x. There's the curve. Now what they want to know is use the graph to predict the value in 4 years. Now x is my years, so I'm just going to go ahead and trace, and do you see where it has that ordered pair? I'm going to trace and try to get as close to 4 as I possibly can. Darn it, I was right there. You want to get as close to 4 as you can, and the y value is what it would be worth. It keeps going over. So I have about 722, you guys have a steadier hand than me, $720.30. Do you see that? So the x is 4, so that's how many years after you purchase the computer. The y value is the value, so your computer would have a value of $720.30. So now you have a worksheet with just a few of these to try on your own. You do not have to worry about sketching the screen for me. You'll just be writing the equation. If it asks if it's growth or decay, please answer that. And then you will just be answering the question using Desmos. I hope you guys had a great time, and I'll talk to you soon. Bye.